And let's think about this problem. So before I start this problem, here's the upshot. So once electric field is given, you can describe the motion of a charged particle. And to do this, we just use Newton's law. Once we know Newton's law, we can appeal to like force is equal to ma. And once you have the acceleration, you can solve it to find the full dynamics. Okay. And I think this is best illustrated with an example. And here's the example. So suppose you have a system like this. Again, this is exactly the same system we solved in the previous week, like this. So this is like a charge plate. One is negative, the other is positive, and an electron of a given mass is accelerating in the uniform field inside here. The separation of the plates is 1.5 centimeters. The electron is accelerated from rest near the negative plate, right over here on the surface, and passes through a tiny hole in the positive plate. Imagine there's just a little bit of hole here, and the electron is shooted to go through that. And the question is, with what speed does it leave the hole here? And B, show that the gravitational force can be ignored. Suppose we have like a gravitational field here, like this, and we need to show that it can be ignored. And we assume the hole is so small that it doesn't affect the uniform field between the plates. So this one doesn't change these field lines, okay? You can take these lines as if there's no hole. Okay, there is 1.03 times 10 to the 7 meter per second. Okay, so electric field is given. Exactly, like F is equal to ma. Let's start with A. So first I need to find the force, and force is, of course, is equal to Q times E, and this will be equal to electron charge. Does anybody remember what the electron charge was? Without looking, of course. I can go back to other pages and write it, but let's try to remember it. Exactly. Minus 1.609, something like that. Maybe 602. I think it's 602. 602 times 10 to the minus 19 coulomb times the electric field. It's right over here. And it is 2.0 times 10 to the 4 Newton per coulomb. And if you multiply these numbers, it is what? 3.2 times 10 to the minus 15 Newton. Okay, this is the force. Now let me use F is equal to ma, exactly like you said. So F is equal to m times A, then A is equal to F over m, which is equal to 3.2 times 10 to the minus 15 Newton divided by m, 9.1 times 10 to the minus 31 kilogram. And we need to remember Newton per kilogram is meter per second square. So this is going to be equal to 10 to the 15 meter per second square. Okay, I think that's exactly what some of you had. Given the acceleration, how do I find the velocity here, right? And somebody already wrote the answer. This is one of your favorite equations. Given acceleration, I can find velocity at any time from this V final squared is equal to V initial squared plus 2 times A times X. And maybe I ask you, like, what is V initial squared? This guy? That's 0. So thank you. Let me choose a different color. This guy is 0. So V final is equal to square root 2 times A times X. And if I put these numbers, 2 times A, I just obtained 3.5 times 10 to the 15 meter per second square times the distance is given somewhere over here, 1.5 centimeter. This is 1.5 times 10 to the minus 2, right? Meter. And if I take the square root of whole thing, my dimensions match. And I have, let's see, this is 1.02 times now 10 to the 15, 10 to the 16 minus 14. Okay, this is like 10 to the 7 meter per second. Let's see, does anybody? Yes, good. I got exactly the same answer. Thank you. Maybe we can calculate the forces. Let me do that just for comparison's sake. So Fg is equal to m times g, which is going to be equal to 9.1 times 10 to the minus 31 kilogram times g is 9.8 meter per second square. And if you multiply these numbers, let's do that. 9.1 times 9.8, something like 8.9 times 10 to the minus 32, maybe 30 Newton. And so this is the force coming from gravity, and this is the force coming from electric field. So maybe I can show it like this. F electric field divided by F gravity is approximately what? It's like F electric field is here minus 10 to the 15, 10 to the minus 15 divided by 10 to the minus 30, which is equal to something like 10 to the 15. So electric field is like, what is this number? I don't even know. So 9 is million, 12 is 100 million, and 100 billion. So something like that, right? It's a really big number. So electric field is 100 billion times stronger than F gravity. So we can neglect gravity. Maybe I can read you the problem and then give you a couple of minutes. So an electron is moving now in a perpendicular direction. In the previous example, this was the direction. And now it is moving along the plate with some initial velocity, which is given V naught. And it enters the uniform electric field at right over here. And we don't consider these sides of the plate. So we just consider a uniform electric field in between. Describe its motion, giving an equation of its path while in the electric field here. And we will completely ignore gravity. Maybe I can go ahead and start because it's almost similar, right? So again, F is equal to Q times E, and Q is minus E times E. And I need to specify this is there's like a minus, so not to confuse. It's like downwards acceleration. Okay. So if I have the force, I can calculate the acceleration. F is equal to m times a. This m is the mass of electron, which was given something like 10 to minus 31 kilogram, very small. And this one will be equal to something like m times, okay, maybe I can do this. Then a is equal to, let's forget about sign and just keep the directions explicitly. E divided by m, again, downwards like this. Okay. So what are we trying to do? We are asked describe its motion by giving equation of its path, right? So this motion is what? This is like a motion in constant acceleration. So we have the equations for that, right? So there is basically an x coordinate and there should be a y coordinate. Can anybody tell me what x coordinate should be as a function of time? So it enters with some velocity v naught, and I want to find x at any exactly, right? V naught times t. So let's write that. V naught times t. And what about y coordinate? Y is equal to 1/2 a t squared. So I can eliminate t from one and put it in the other one. Let me eliminate t from here. T is equal to x divided by v naught, and plug in on this t. Then I'll find y is equal to 1/2. My acceleration is given here, something like this. E over m times, this is x squared over v naught squared. And this is like y is equal to alpha times x squared. This is a parabolic path. And you are familiar with this, right? We spend a lot of time with that kind of path. Now I want to introduce a new concept. I want to tell you about electric dipoles. Let me just clean some of these guys up. Okay. So the dipole is a system of two charges, right? There's like a negative and there's a positive charge, and we consider them to be bound together. And there's like a distance between them, which we call it L. And this bound system is called electric dipole. And if the magnitude of charges are like plus q and minus q, and the separation is L, like this, then we define something called dipole moment. And its definition is like a vectorial form. P vector is equal to charge, which is a scalar number, times L, a vector from minus charge to plus charge. So basically, dipole is a vector that points from negative charge to positive charge. So why do we need something like this? We need things like this because actually they are very abundant in nature. And one example is water molecule that we are familiar with. It has a non-zero dipole. So basically, water molecule is composed of one oxygen and two hydrogens. And there is like a charge separation in this molecule. Oxygen is mostly negative and hydrogens are mostly positive. That's like an ionic molecule. And if you consider the definition of dipole, there's actually a dipole here like this, another dipole like this. And since these two are vectors, we can make a vector addition to find the net dipole here. And this angle happens to be about 104 degrees. Okay? So once you have a system like this, we also need to specify its motion, its dynamics. And for this, we need to specify two things, right? We need to specify first the net force. Maybe I can ask you, deleting this, what is the net force? Let's think about an arrangement like this. We have like a constant acceleration pointing in x direction. and I want to consider a dipole like this. Let this be my dipole with some arbitrary angle theta. And I want to find the net force on this dipole. How do I do this? Now I want to ask this question. I have a uniform field, and I have a dipole formed by two charges, plus q minus q, and I want to find the net force. How do I find the net force on a dipole? Yes, it's 0, and the reason is basically I can write the force on the first charge, which is q times E. I can write the force on the second charge. It's because it's in the opposite direction, it is going to be minus q times E. And if I add these two things up, it's equal to 0. So there is no net force as long as the electric field is uniform. Of course, if the electric field is not uniform, that means electric field here may be different from here, then there may be a net force on the dipole. So we have to be careful about this. So once I have 0 net force, I know translational motion is frozen. There is no translational motion. How about rotational motion, right? For the rotational motion, I have to find the torque. And for torque, I mean torque with respect to center of the dipole. How do I find that? Yes, like it is like, let me try to remember. It is force times perpendicular distance, right? And maybe F total times perpendicular distance. And in this case, force is, for example, this one is Q times E, and the perpendicular distance is something like this, right? Or I can think about perpendicular force, which is like 90, and the distance, which is identical. And to find this distance, I have what? Maybe I can write this. So clean this part. It's going to be Q times E times the distance to the center is, so this total length is L. So this part is L over 2. So this is L over 2. And to find the perpendicular distance, I just multiply with sine theta. And I have another contribution coming from here, right? This guy is trying to rotate this clockwise. This guy is trying to rotate this clockwise. So let's put this in. Plus, because they are trying to rotate in the same direction, Q times E times L over 2 times sine theta, which is equal to, if I use like the definition of dipole, which was Q times L, right? This is P times E times sine theta. But I told you dipole is a vector. An electric field itself is a vector. And we can write this thing as a vector product, right? Like a cross product. And then the definition of dipole is like this. Tau vector is equal to P cross E. Actually, E is also a vector here. And here I want to remind you, right-hand rule applies to this too, right? If you want to find the direction of torque, you use your right hand and you start with P and then go through E. And if you stick your thumb out, you're going to have the direction of torque. For example, here, I start with my fingers along this, and I curve my fingers like this. And if I stick my thumb out, it's going to be into the page. So that means the rotation will be clockwise. Okay, once I have the torque and net force, I can calculate the net work done on dipole by the electric field, right? So that's what this means. This is work done on dipole by the electric field. And how do I do this? How do I calculate this? What was work? Does anybody remember? F times X, right? So it's like maybe F times dl, but we know force is 0, net force is 0, so I can forget about this. Does this mean it's 0? So the net force is 0. So does this mean the net work done on dipole by electric field is 0? Exactly, right? It could we could be doing rotational work, and the form of rotational work is exactly like F dot dl, but here F goes to torque and dl goes to rotational dl, and rotational dl is what? D theta, right? D theta. And let's apply this to this form. For this picture, actually it's rotating along this direction, so it's going to be minus d theta, right? And my torque is equal to, maybe I can write it like this. My torque is equal to P E sine theta, and suppose it goes from some theta 1 to theta 2. Okay, and this one should be equal to P times E. So minus sine theta is cosine theta, and if I put the limits, cosine theta 2 minus cosine theta 1. If you remember our vocabulary, like we describe force, torque, work done, and now we can talk about other things in our game, right? We have like something like potential energy. And remember that if you have like a conservation, conserved force field, you could define a potential energy. And here we have a conserved field, conservational field, electric field, exactly like gravity. There's no difference almost. Then we can define potential energy was the minus the kinetic energy. And let's suppose we are thinking about, like, I think it's kind of arbitrary where we put the 0, but suppose we are thinking about theta 1 is equal to pi over 2. We start from here and we go to some, okay, this is theta 1. This is some theta 2. Let's call this theta, and let's call this pi over 2, okay? And I want to calculate the potential energy difference between these two. And it is minus because we are rotating like here, right? This is theta, and this dipole, I mean, this is plus, so this will go this way. This is minus, this will go this way because electric field is this way. Then this dipole is going to rotate this way. And what does this mean? We generally take, like, let's remember angular coordinates. If you have like a circle like this, you can put your axes, something like this. And if you are on a circle, so this is theta in this direction, and this is d theta, again, this direction. But if you are talking about the opposite directions, you have to put a minus. That's what's happening here. That's why I put a minus sign here. So I was talking about the potential energy and potential energy with respect to this, right? Potential, we generally have a reference point for potential. And my reference point is like this. I want to start from here, which is theta is equal to pi over 2, and go to some arbitrary angle. Okay, this is pi over 2. This is, let's call this theta is equal to some theta. Okay, maybe this is theta 1, this is theta 2. And I want to calculate u for this initial to final, right? And I can use just this guy. So initially, okay, there's like an overall minus sign because of work energy theorem. Minus the work is equal to energy, potential energy. So that's this minus. And now I should just copy this guy, but my initial angle is, this one is pi over 2, and this one is theta. So the whole thing becomes minus p dot e, right? So this is like cosine. So I just put p dot e cosine. And this is also, I want to point out, this is also for non-uniform electric field. Actually, this whole thing is for non-uniform electric, sorry, the uniform electric field. If your electric field has any inhomogeneity, if electric field here is different from here, you have to keep an integral in all of these expressions. But I think we are not going to do that in this class. But if you have the appetite, you can go ahead and convert all of these expressions to integrals, right? And there'll be a net force, and torque will be a little different, work done will be different, all these things. So here's another example. So let's think about the dipole in a field. And in this example asks for a dipole moment of water molecule is something like this. And we place a water molecule in a uniform electric field with magnitude given by this. And we would like to calculate the magnitude of the maximum torque that the field can exert on the molecule. And B, what is the potential energy when the torque is at its maximum? And we say, in what position will the potential energy take on its greatest value? And it says, why is this different from the position where the torque is maximum? Okay. For this argument, let's just continue with previous example. Let's say these are the electric field lines, something like this. Let's say they point like this. And I would like to place a dipole like here, maybe like this. And this dipole is known, E is known, and I'd like to calculate the maximum torque. So the torque is, right, P cross E, or I can just write this like P E sine theta. So to maximize the torque, I should maximize sine theta, and maximum of sine theta is what? It's sine theta is 1, yes, for theta is equal to pi over 2, and this means dipoles should be something like this, right? Like they are perpendicular. In this case, tau max is equal to just P dot E, which is equal to what? 25 minus 20, 10 to minus 24. How about that? Is that correct? Yes, good. So B, what is the potential energy when the torque is at its maximum? Potential energy at theta is equal to pi over 2. I think we just found what? minus P dot E. And if these guys are perpendicular, this is 0, right? Since P is perpendicular to E. And there's a follow-up question. What is the potential? In what position will the potential energy take on its greatest value? And why is this different than the position where the torque is maximum? Okay. And the question C. So U is equal to minus P dot E, which is equal to P E minus cosine theta. And minus cosine theta is maximum of 1, right? If theta, okay, theta is equal to minus pi, then it's equal to P times E. And this means dipole moment is perpendicular, like anti-parallel. Maybe I'm not sure how to show this. Maybe I can show it here, not to mix things up. So if this is your electric field pointing this direction, your dipole should be pointing this direction for maximum potential energy, right? So, so far I was thinking about a dipole in an electric field, but another question we can ask, dipole is formed of these charges. These charges have their electric fields, right? And what is the electric field coming from dipole, right? Actually, we showed these electric field lines. They were like this. And they were like this. So at a given point, what is the electric field? And we can calculate that. Maybe I can write it here. So let's just consider this example. I have a charge minus Q, another charge plus Q, and I want to find the electric field right on this line, somewhere around here, okay? So let's say the distance is R, and the dipole is separated by dipole length is L. So I want to find the electric field. So the electric field will have two contributions, one coming from negative charge, because this is negative, this one will point this direction. There will be another contribution from positive charge, because this is positive, it's going to point this direction. And if I sum these two guys up, I'll have a net electric field along this direction, right? And let's find these guys one by one. First, the plus charge, it is some K times Q divided by distance. And the distance is, I can just use Pythagorean theorem, square of this plus square of this, square root. It is going to be R squared plus L squared over 4. And the second one is, maybe I can also find the projection, because this guy will have a component like this, and I will need to sum these up. So to find the projection, I just multiply with cosine, and the cosine of this angle is cosine of this angle, and cosine of this angle is just L over 2 times, sorry, L over 2 divided by this. So let's write this. L over 2 divided by square root R squared plus L squared over 4. So this whole thing becomes K Q times L over 2 divided by R squared plus L squared over 4 to the power 3 over 2. So I can do the same thing with this guy. let's do this. And to make sure the direction is to the left. So the second one is again k q divided by r squared plus l squared over 4. Exactly the same thing. Q divided by this distance squared, which is this squared plus this squared. And I need to find cosine. Cosine of this angle is cosine of this angle. Exactly the same story. It's L over 2 r squared plus L squared over 4, which is k q L over 2 divided by r squared plus L squared over 4. This is also to the left. Now I can sum this plus this, which is what? Maybe I can write it k is equal to 1 over 4 pi epsilon naught. So I have q times L over 2 plus q times L over 2, which will be equal to q times L. But I know q times L is equal to P. Let's just write it P for short. This is P divided by, and the denominators are the same, this guy and this guy. So this, I forgot the cube here. So this is going to be r squared plus L squared over 4 to the power 3 over 2. And that's the final result, right? And now I want to consider some limit. Suppose I am really far from this dipole. Suppose I have a dipole here, like I'm very far from the dipole. But I am interested in this position. The dipole is perpendicular to this line I'm looking at. Like I'm looking at dipole exactly from its cross section. And that limit is what? That limit is R should be much, much, much greater than L. Then I can just forget about this factor because this is very tiny. And the E total will be, or E dipole will be something like this, 1 over 4 pi epsilon naught P divided by R cube, right? Now I want to remind you the list of things we have now. I think we have some interesting results in retrospect. First, let's start with a point charge. And if you have a point charge, we know that's our beginning point, right? And it's like the electric field of a point charge is 1 over 4 pi epsilon naught Q over R squared. So if you have a line charge like this, at any given point, like along this circle or any circle, of course we are assuming an infinite line, the electric field is radially out if this is positively charged, and the electric field is radially in if it's negatively charged. And its magnitude is interesting. It's 1 over 2 pi epsilon naught times lambda over R. So, right, it goes from R squared to R. And this lambda takes over for Q, which is the charge density, charge per unit length. So we had like a ring. I think, do I have the ring? Maybe we don't need ring. I could write it, but it's not simple. Maybe I can think of like this planar charge, which is nicer. If you have a plane that goes in all directions, right? And for the argument's sake, let's suppose this is like a positively charged plate. So the electric field is always perpendicular to the surface, and it is independent of the distance. sigma over 2 epsilon naught. So far we had all of these results already, and the final addition to this list is electric field of a dipole. So this is a little bit more complicated than the previous cases because it's like a system of two charges. One is negative, the other is positive. And if you are far from the dipole, electric field goes like 1 over r to the cube, right? That's what I'm trying to, this is r squared, this is r, there's no r here, and for dipole, there's like 1 over r cubed.